Okay, we're going to talk about a few more graph transformations today, and we're going to talk about vertical and horizontal stretches and compressions. And then we're going to talk about the order that we have to do all of our transformations in. And that becomes really important. So for a horizontal stretch or compression, I'm going to show you how the book does it, and then I'm going to show you how I think of it. So they do x over c inside. So it has to be inside the function. So if it's squared, it's got to be on the inside. And they're using c greater than 1 stretch c less than 1 compression. I find this way hard. What I do is I think of it as f of cx. So I'm just leaving it on the inside. But c, really, these should be between 0 and 1. Okay. I switch those. Let me do this in red, actually. This is how I look at it, because usually it's actually written like this. C greater than 1 is a compression. Compression, or another word for compression is shrink. So we're condensing all the ones. C between 0 and 1 is a stretch. Because usually what they're going to give you is if your function is f of x cubed, you're going to get transformed function of, say, 2x cubed. Functionally, this is going to do the same thing as a vertical stretch, but because I could expand that to be 8x cubed, which is a vertical stretch. When it's outside, it's vertical. When it's inside, it's horizontal. But let's look at what it does to the points, because I want to talk about the points, because this is going to come up later when we do transformations on trig functions like sine and cosine. This is where horizontal and vertical separating them becomes important. With this, well, I could just really make it that. So looking at a point on the original, so this is my x, and this is y equals x cubed. We're going to look at what it does point by point. So x, we'll do 0 doesn't matter. 1, 2, 3. No, we're going to avoid 3. We're going to do 4. Okay. So, and then my factor here is 1 over c, which is why the book writes it as x over c, but I think it's more confusing to think of it that way. Okay. So here, x cubed, 0, 1, 8. 4 cubed is 64. I'm going to my transformed 2x cubed. I'm going to use the same x coordinates. Or I'm going to use my transformed x coordinates. Because this is a horizontal, I need to change the x coordinates. So instead of 0 still stays at 0, I'm dividing by my 2, okay? Dividing by my 2 here, 1/2. 1 becomes 1/2. 2 becomes 1. 4 dividing by 2 becomes 2. And my coordinates stay the same. Okay, so really what I'm doing is I'm taking my x coordinates here, and I'm transforming them over here by dividing them by a scale factor of 2. On a graph, I'm not going to graph the 64. It's just too big. So my initial function, we're going to do in red. 1, 2. 1, 5. And my cubic looks like this. In general, cubics look roughly like that. My transformed one, 0 doesn't change. It looks a lot tighter. Oops. Not a very good drawing there. Let me try that again. It's so tight you can barely see the inflection on there because I didn't draw it perfect. But so that's a horizontal compression. I just pushed each point in half as much. A vertical stretch for this, we can do the same thing in a vertical stretch. Vertical here, stretch or compression, is f of, no, but c f of x. So it's on the outside. So inside the function here, I was applying this, putting it inside and then cubing it. This one, c is greater than 1, is a stretch. C is between 0 and 1. The negatives do reflections, so this is why I'm putting it between 0 and 1, is compression. The sign on C is not part of this. The sign tells me whether I reflect, which we talked about earlier in the week. So here, I'm going to take my original XY table, and now we're going to do, so I'm going to show you that this could be the same. Take my original XY table, now I'm multiplying my Y values by 8. So vertical stretch literally takes the graph and multiplies each Y value by 8. So 0 times 8 is still 0. 1 times 8. 2, 8 times 8 is 64. 64 times 8. 512. Notice that these points are the same. Vertical stretches and horizontal compressions tend to look about the same in a lot of cases. You can accomplish the same thing by doing either one, mostly. The change being sometimes if they're crossing the axes. So the function here, this is the function given in the book. And the graph looks like this. It has x-intercepts at -4, 0, and 4. Let's put those in a different color. So here's my original graph here in blue. I'm intentionally not putting any y coordinates on here because I think it gets higher. I don't think they later. Yeah, I think they went by tens actually on the y's. So I can pretend to do that. This is 20, roughly. Roughly negative 20 down here. And then that's my graph. My blue one is that one. I'm going to do a purple one now. And we're going to do a vertical stretch. So this is 3 f of x. If I actually apply that to the function, I'm distributing the 3 to both parts. What am I doing? I'm multiplying each y coordinate by 3. That does not affect my zeros. What it does affect is my max that's hitting around 20 is instead going to be up around 60. Instead of down at negative 20, I'm going to be down at negative 60. And my graph just becomes stretched out and steeper. Okay, if I do a shrink by a factor of 1/2, that's going to look like this. Okay, and again, it's inside. So that looks like there should be an X there. So that means I'm cutting each X coordinate in half. 0 stays the same, but my intercepts, instead of being out at -4 and 4, come in. The height of my original does not change. It just gets narrower. Assume that I'm drawing these straight and the heights of these maxes and mins here on the blue and the orange one are the same. You can see a nice drawing on page 145. So that is vertical and horizontal stretches and compressions. Okay. It is important now when we put things in multiple translations to do them in the correct order. Okay. So we're going to take a look at pretend our parent function is y equals x squared. And I'm actually going to add more than the example does. And we're going to transform this so I've got a bunch of transformations. We have reflection over y-axis. No, sorry, that's x-axis. Inside is y-axis. So reflection over y-axis. Essentially, I'm flipping my parabola down. We have vertical stretch of 3. Right here, I have a horizontal shift. Remember that when I'm inside, I go opposite the directions. Horizontal shift to right. So this one is 2 to the right. And then finally, I have the vertical shift or translation. Shift, translation, same thing. That one's up 5. So the order I must apply them in. 1 and 2 can switch. It's kind of like multiplication, division, reflections, and vertical translation, vertical stretches and compressions, horizontal stretches and compressions can all switch. Horizontal shifts and vertical shifts can go in either order if you kind of just, I usually do them together. So I'm going to show you, I'm going to do 1, 2 in the same step. So here's my original graph. Y equals x squared. I'm going to do specific points. This is 4. So 0 squared is 0, 1 squared is 1, 2 squared is 4. Same with the negatives. I get a nice parabola. The negative flips it down and each point goes down. And then, so I'll just flip it down. This is translation 1. Now my vertical stretch here, I multiply each one by 3. So instead of being negative 1, 1, negative 1, and negative 1, negative 1, I'm now 1, negative 3. This is 5. Instead of being 2, 4, now I'm multiplying 4 by 3. I'm multiplying the y coordinates by 3 because it's a vertical stretch. And now I'm down. I will apply both my vertical and horizontal shifts. So I'm going right 2. I'm going to take this graph, move it over right 2, and then up 5. Take this point, move it right 2, and up 5. Take this point, move it right 2, up 5 to negative 7. And there is my graph. Okay. We can do these same things with geometric ones. Example 7 shows doing that. And literally, they're just multiplying all the points. They're applying it point by point. Okay, there is your lesson for today.